In the last session, we have seen how to calculate the distribution factor. Today's session, we have discussed about the harmonics and its impact on coil span factor as well as the distribution factor. Once again, we can recall the distribution factor, the derivation. That is, if there are three coils were bunched in one slot, that is, for these are the slots under one pole. Then one slot is meant for R, another slot for Y, the third one is for B. Then all the conductors pertaining to the one particular phase, if you are placing in one of the slot under one pole, then what we are getting is the three coils are bunched in one slot, then the total EMF induced in these coils would be the arithmetic sum. Because as such there is no phase displacement between the conductor which is placed in only one slot, then the total voltage what we are getting is the arithmetic sum. That is, you can see here, that is voltage induced in one of the coil, the voltage induced in the second coil, the third. These are all they are placed in a single slot. Therefore, the voltage, the total voltage what we are getting is 3 times ECS. The such type of winding is called as concentrated winding. These are called as concentrated winding. Suppose if there are the slots, for example, if we are taking here, there are around 9 slots, we'll get it for 9 slots for each pole here. That is the number of slots for here. There are 36 slots and there are 4 poles. There are 9 slots, 4 poles, 9 slots per pole. Out of these 9 slots, then 3 are for R, 3 are for Y, 3 are for the B. In the previous case, you have got only one slot for R, one slot for Y, one slot for B. But in this case, the coils of one particular phase is spread over the different slots. Therefore, you can see here, these are the different slots which is assigned for R phase, B phase and the Y phase. Then now the conductors are distributed in of a one particular phase in the different slots. Then it is called as a distributed winding. Therefore, then the angle between the adjacent slot, what we are calling is the beta, the angle between the adjacent slot. Then how we are finding out? For this particular example, there are 36 slots, therefore there are 4 poles, therefore then how many slots you can assign to the one particular pole? That is 36 divided by 4. There are 9 slots are assigned to the one particular pole. Out of 9 slots, once again you have to redistribute those 9 slots for 3 different phases. One is for R, Y and the B. Means the number of slots per pole is nothing but a pole pitch which is equal to 180 degree. Which is equal to 180 degree. Therefore, for 180 degree electrical, the total number of slots in this particular case, they are 9 are distributed. The 9 are for this particular pole. Therefore, 180 divided by 9, that is the 20 degree. Then how to find out the slot angle? The slot angle can be calculated by, it is beta is equal to 180 divided by the number of slots per the pole. That is the angle beta. Means one conductor is placed in the slot number 1, second conductor is placed in the other slot, and the third one is other slot in a same phase. There is a phase displacement between these coil sides, that is a beta here, beta here. Therefore, here the total induced voltage for particular R phase is sum of the voltage induced in the first slot coil, second slot coil, the third slot coil. But however, they are not in phase, but they are displaced by the beta degree. Therefore, there is a vector sum. This type of winding is called as the distributed winding. Therefore, here what I am doing here is ECS, ECS and the ECS. They are all displaced each other by an angle of beta, that is in this particular case it is 20 degree. Therefore, we are getting a resultant voltage. In the concentrated voltage, it is arithmetic sum. In the case of distributed winding, the total voltage what we are getting is the factor sum. Therefore, the distribution factor is defined as it is a voltage induced in the distributed coil to the concentrated coil. Then that is a general equation it is which is derived in the last session. That is beta is the angle between the slots, that is given by 180 divided by the number of slots, or in general beta is equal to 180 divided by n. M is the number of slots per pole per phase, means the number of slots per pole per phase. That is, you are seeing in the last the figure, that is there are 36 slots. First you are distributing 36 slots for each pole, that is 9 slots per pole. Out of 9 slots, it is once again distributed for 3 phases, that is becomes your M. Then the M beta is a phase spread. The M beta is the phase spread, means how many slots per pole per phase. The angle which is spreading over from here to here, that is one particular phase, then it is called as phase spread. That is M beta is called as a phase spread. Now in this case, the how many slots we are getting for the one particular phase? There are M number of slots are we are getting for each phase under each pole. Therefore, the phase displacement between the phasors is once again the beta, and how many number of vectors you have to add, that is M number of vectors you have to add, therefore with beta each other. Here I am shown only 3, then AE gives the total induced voltage, that is a vector sum of M number of vectors. Then I made a construction line here and dropping a perpendicular from the AB, and I am finding out the what is AB in terms of R, that is, and also I am finding out, I am dropping a perpendicular from the resultant AE, and once again I am finding out AE in terms of R and M beta, here beta by 2. Therefore, what I am getting from this particular triangle, that is AB, that is the total AB is nothing but it is 2 times from the center drop point, it is center point. Therefore, I am calculating now only this, or you can call this as that is, you can call this as M. In that case, the AB is equal to 2 times AM. Therefore, from OAM, you can find out what is AM, that you are getting is R times sine beta by 2. Therefore, it is 2 times AB is 2 times AM. Therefore, 2 times sine 2R sine beta by 2. What you are getting here. Similarly, for triangle AEO, then I am dropping a point here. You can call this point as N here. Then from triangle OAN, there is AN, you can find out this is totally M beta, this is M beta by 2. You can apply once again sine function. Therefore, that is AE is nothing but 2 times AN. Therefore, what I am getting is 2 times R sine this arithmetic sum, that is for this triangle. For second one, vector sum is it is 2R sine M beta by 2, because I am taking triangle ANO, find out AN, then you multiply 2 times. Therefore, what we are getting is AE. Therefore, what I am getting here is it is the arithmetic sum to it is vector sum to the arithmetic sum, or it is a voltage induced in the distributed winding to the voltage induced in the concentrated winding. What we are getting is sine M beta by 2. Then we will take up one numerical on this particular factor. Calculate the distribution factor for 36 slots, 4 pole, single layer, 3 phase winding. For this, you have to find out the KD. That is, first you have to write KD, that is sine M beta by 2 divided by M sine beta by 2. You have to find out M, that is the number of slots per pole per phase. Beta is the slot angle. Then we know that the number of slots per pole is 36 divided by 4, that is 9. Then the slot angle you can calculate, it is 180 divided by n. 180 divided by n already we have calculated as a 9, therefore it is 20 degree. Then m is the number of slots per pole, or m is n by 3. M is equal to n by 3, that is number of slots per pole per phase. Then what we are getting is 3. That is, we know the value of m, we know the value of the b, just have to substitute and find out the value of kd. Kd, what we are getting is 0.96. Then what do you mean by the harmonics? Then what is the impact of this harmonics on the distribution factor and coil span factor? In turn, it is affecting the total induced voltage in the three-phase alternator. We know that the standard sine wave, which is ideal, is not always attained in a practice. Some are other reasons. Some are other reasons is because of the field system, which is not non-uniformity. Okay, then the conductor, then non-uniformity of the air gap. Because of this, the waveform which is generated in the synchronous generator is not a sinusoidal waveform. However, it is a periodic waveform. It is a periodic waveform because the all other are symmetry, but they are not getting a pure sinusoidal waveform, but they are getting a periodic waveform. That is, so what is our object is to get the pure sinusoidal waveform. But it is usually not getting in practice, but we are getting a periodical nearer to the sinusoidal waveform. We are getting the waveform from the alternator. If the waveform is non-sinusoidal, however it is a periodic, that can be resolved into sinusoidal waveform for analysis work. I'll repeat once again, that is, any periodic waveform can be analyzed by resolving periodic waveform into the sinusoidal waveform with a different frequency with different amplitude. Such components are called as the harmonics in the system. The same thing is written here. Any periodic wave can be analyzed mathematically into number of pure sine waves of a different frequency and the amplitude. The head of the component, that is the main component, which has got the same frequency that of the original waveform, periodic waveform, that is called as a fundamental. That is, the head of the component wave is called as a fundamental, has the same frequency that of the main waveform or the resultant waveform. The other components have frequency that are exact multiple of this fundamental frequency. That is, if we are resolving the periodic waveform with double the frequency of the fundamental, then it is called as a second harmonic component. Then another component we are extracting from the same periodic waveform with the 3 times the frequency of the fundamental, then it is called as the third harmonic component with a different magnitude. Then when if we are combining all these harmonic components, once again we are getting the original periodic waveform. Periodic waveform is not a sinusoid wave. A wave consisting of both fundamental and harmonics is said to be non-sinusoidal or distorted waveform. It is called as a distorted or non-sinusoidal waveform. Then only you can extract a sinusoidal waveform out of it and you can analyze. And if you are combining, once again we are getting non-sinusoidal waveform. But in the case of pure sinusoidal waveform, you don't have any component because it is pure itself. It has got a pure sinusoidal, as such there is no harmonic content in the pure sinusoidal waveform. The harmonic has 3 components. Is the property if you are extracting a different frequency, different amplitude, the component from the periodic waveform, then it has got 3 different characteristics. One, they have got a different frequency, different amplitude, and there is a relative phase displacement is also that different. That is, waves having frequency of 2f, 4f and 6f etc. they are called as even harmonics. Waves having frequency that is 5 times f or 3 times f or 7 times f, because these are containing the odd component of the harmonics, therefore they are called as odd harmonics. In electrical engineering, the wave shape of the voltage generated is mostly symmetrical, but it is not a pure sinusoid term. Due to the fact that the field system armature coils are symmetrical, therefore generated voltage or a current have no even harmonic. Therefore, how the harmonic component changes impact on the coil span factor and the distribution factor, that we will see. Before looking into that, just I told you this is our non-sinusoidal waveform, but however it is symmetric, means both positive cycle and negative cycle having the same. Out of this main waveform, we are extracted one component with a pure sinusoidal waveform with the same frequency as the original waveform. Then it is called as a fundamental component of this waveform. Fundamental component of this waveform. And another component here I am shown with the 3 times frequency that of the original waveform. Then it is called as a third harmonic component. Only I extracted 2 components. If I am adding the fundamental and third harmonic component, I am adding, then what I am getting is once again original waveform, original non-sinusoidal waveform. In other words, a non-sinusoidal periodic waveform can be resolved into sinusoidal waveform with the different frequencies and different magnitude. These are called as the harmonics. Then, if we know that the pitch factor is given by cos alpha by 2, then if there is a harmonic content is there, if it is non-sinusoidal waveform, in that case the alpha is become 3 alpha for the third harmonic, 5 alpha is become for the fifth harmonic, and so on. In general, if there is a h is the order of the harmonics, then your kch is becomes cos h alpha by 2. Or for example, for fundamental h is equal to 1, it is cos alpha by 2. For fifth harmonic, it is h is equal to 5, therefore 5 alpha by 2. For third harmonic, h is equal to 3, therefore kc 3 is equal to cos 3 alpha by 2. This is for the third harmonic. This is how we have to calculate the coil span factor for the different harmonic. Similarly, the effect of harmonic on a distribution factor is once again the same. That is, the distribution factor is also different for a different harmonics. Its value in general, it is written as sin hm beta by 2 divided by m sin h beta by 2, where h is the order of the harmonic. Therefore, for the fundamental component h is equal to 1, therefore your kd1 is sin m beta by 2, m sin beta by 2. For third harmonic h is equal to 3, therefore it is sin 3 m beta by 2 divided by m 3 beta by 2. Similarly, for the fifth harmonic, that is sin 5 m beta by 2 divided by m sin 5 beta by 2. This is how we have to analyze and you have to see the effect of the harmonics on the coil span factor and the distribution factor. In the next session, we will derive the EMF.